Hello everyone, this is Juan Fraire, and in this talk I'm going to present our GlobeCom paper entitled Sparse Satellite Constellation Design for LoRa-based Direct-to-Satellite Internet of Things. So a brief overview on the agenda we're going to follow today. We're going to go over a quick introduction on the topic and the motivation to go into details about direct-to-satellite IoT. We're going to define what this concept is, and then we're going to introduce sparse DTS IoT concept, which is one of the contributions of this paper in terms of concept. And then we're going to describe and discuss how the DTS IoT satellite constellations can be designed. We're going to propose and formulate a formal model for this. We're going to propose a gradient descent solutions, and when we're going to overview the results so we can evaluate which is the real contribution of DTS IoT. So everyone knows that Internet of Things is on the hype at the moment, and we are expecting millions of devices to be connected in short term. And for this, we see that we have at the moment short, medium, and long-range protocols that are already available to cope with this challenge. Achieving a global IoT service remains still an open issue. We do have long-range protocols, but we don't have long-range protocols that are capable to connecting the whole planet. So to this end, we believe that satellites can be a game changer for this, and in particular when satellites are used in a direct-to-satellite IoT where devices directly access the satellite, we say that we can leave behind intermediate gateways on ground and just get the device to continuously directly connect to the passing by satellite. This is something that already exists. Physical and link layer solutions has already been evaluated by LacunaSat 1, and it is the satellite we see here on the picture on the right, and that the ground devices using standard IoT protocols such as LoRa can access this CubeSat and relay data to the passing by satellite. One of the challenges that remains is how do we actually design constellation of the satellites in such a way that we can leverage the delay tolerance aspect of this IoT network, and also while complying with the bounded clock drift period of inexpensive devices such as the one we see here, while still getting a synchronization between the satellite and the device. We frame this problem under sparse constellation design, and we show that by means of a gradient descent method, constellations of less than 10 satellites can already be providing direct-to-satellite IoT services instead of thinking on very large satellite constellations such as Lacuna mentioned in the order of 240 satellites. This is the concept that we present in this paper, and we're going to overview this gradient descent method at the end. So a little bit of background for this. So in this plot, we see the distance of the link on the x-axis, and we see on the y-axis the bandwidth or the data rate that are expected in these networks. Low power wide area protocols such as LoRa, NB-IoT, or Sigfox are already pushing forward very long distances for IoT links, which are naturally low bandwidth, low data rate links. But if we want to think on a truly global IoT, then it's better if we can still think on satellites that can provide unprecedented coverage. We compare with any type of ground stations or base stations from LPWA networks. So direct-to-satellite IoT also needs to leverage traditional satellite networking expertise so that links can be successfully established at very big distance, like for instance in the order of several hundreds of kilometers, such as when we talk about low Earth orbit satellites or LEO satellites. So existing LEO systems already designed, so we see on these traditional satellite networks, are already providing voice and internet service to ground, and they are already leveraging machine-to-machine communications protocols to provide some kind of IoT communications. And then on the other spectrum, we also have some new LEO systems that are leveraging chips CubeSat, such as the one we have seen on the previous slide, which are very small and cheap satellites, to provide effective DTS IoT services and compete with these very big companies that are already providing voices and internet services. Direct-to-satellite IoT, compared with indirect, as we mentioned, uses a direct-to-satellite link to the devices on ground instead of relying on an intermediate gateway, as we can see here on the figure on the left. In this work, we argue quite in favor that LoRaWAN, among the mentioned LPWA protocols, can actually be quite attractive for satellite links and for the direct-to-satellite IoT for many reasons. LoRa actually provide very low power and very large link margins that can already close a SATCOM link even from the device to the passing by satellite with minimum modifications to the antenna or the link budget computation. LoRaWAN does not depend on regulations, therefore frequency assignations do not need to be regulated, so this implies that device service can be deployed easily than compared with other systems. They have proven feasibility because of the LacunaSat-1 and future satellites already on the launch pad, providing LoRa services from satellite, namely the physical link and the link layer are already tested from orbit, which is also favoring quite interesting features for LoRa as a candidate for providing DTS IoT services. On top of this, LoRa can provides unprecedented MAC layer flexibility because the LoRa physical layer is a proprietary layer which is typically untouched. But on top of that physical layer, there is quite a lot of flexibility to design MAC layers that can suit different types of communications. In particular, we would like to focus on Class B, which is a beacon mode for LoRaWAN. And we believe that this Class B structure can actually be profited for satellite communications because of a beacon that can be conveniently used for devices to know when a satellite is going to pass by. Class B has a beaconless mode that allows devices to remain disconnected from the gateway, namely the satellite in this case. So there will be some kind of gaps between satellite passes, and this gap shall not be longer than 2 hours in the case of LoRa, right? And the reason for this is because the clock of these cheap devices will drift and the synchronization will be lost. But this still gives us quite a new opportunity to describe what is a sparse DTS IoT. In a sparse DTS IoT constellations, satellite coverage is not continuously provided like in traditional constellations, but we have gaps between this coverage, and the condition is that this gap shall not pass this bound time limited by the clock drift of the devices on ground. So to this end, the question we want to answer is then how do we actually design such a constellation in such a way that we can comply with this maximum beaconless gap period? So we have formulated a constraint programming optimization model with specific variables, namely independent and dependent variables that tackle this problem. We have leveraged specific coverage models and we evaluate access to the agreed of latitude and longitude points located in strategic parts of the surface, which are the evaluation element of the model. We also leverage some analytical equations that we discussed on the paper for relating the inclination of the orbit that are going to be utilized by the model. And we state a search space based on the number of satellites, the number of planes, and the inclination of the orbit, among which we will try to get an optimal parameter of the constellation such that the beaconless gap between satellites is never higher than 120 minutes. And then also we want to minimize the number of satellites, such as we can understand, which is the size of the constellation that a sparse DTS IoT constellation needs to have in order to provide the required Class B beacon-based LoRa service we have described. We have made some assumptions that simplifies the model, such as all satellites in the constellation shares the same inclination, height, and swath. Also, all the satellites in the constellations uses circular orbits, and there is an homogeneous distribution of the orbital plane throughout the equatorial plane, and all the satellites are also homogeneously distributed along the single plane. Considering this formulation of the model, we proposed a complexity progressive gradient descent algorithm that basically brings SGP4 orbital propagator into the loop of the optimization strategy. And we are able to compute access based on these trajectory computations. And during this access computation, we evaluate different solutions of, along the search space we proposed. And we are able to come out with quite interesting constellation configurations suitable for DTS IoT on the sparse version, as we have mentioned. These are the results and also the conclusions that we got from our work. So we studied in particular orbits from 700 kilometers height, namely LEO satellite orbits, and we have studied 60-degree latitude coverage and also 80-degree latitude coverage constellation formulations, which we found to be not so sensitive. Basically, the tendency between these two plots here on the left and the right are quite similar. But within each plot, we analyze which is the number of planes and satellites, namely the size of the constellation on the y-axis, versus the elevation threshold or the swath width, namely the coverage of the antenna of the LEO satellite on the ground. So you can see here three particular example solutions of that was found by our algorithm, and you can see that as soon as the coverage of the antenna gets wider, then we get also a reduced number of satellites required to provide the gap period required for this DTS IoT constellation. It is interesting to see that, as I mentioned, so the number of satellites increased with lower swath and elevation limit. This is a natural intuition that is confirmed by the experiment. Also, the maximum latitude is rather insensitive, as mentioned, on the plot on the left and on the right, show here. But inclination, which is tracked in this red curve, also quantified on this right-hand y-axis, does play a major role in the coverage of the DTS IoT constellation we have mentioned. What is important to read from this plot is that, as we can see, like 9 satellites in a sparse DTS IoT are already able to provide service using this beaconless mode we have proposed, and to provide similar service with a dense DTS IoT constellation, we would need around 88 satellites. This relation rises up to 40 in DTS, in sparse DTS IoT, and which compares with more than 800 satellites required to provide a continuous DTS IoT service using continuous coverage, such as in traditional constellations. So, as a conclusion of this work, we say that sparse DTS IoT can operate with a real minimum amount of infrastructure in comparison with dense DTS IoT infrastructures. We see from this plot that around 4% to 10% of the infrastructure is only required. And this implies, and in practical, this means that even though the latency of such a sparse DTS IoT constellation will be higher than the latency of a dense DTS IoT constellation, this still means that this type of service can already be provided by DTS IoT constellation as the satellites are being deployed in time. So this means that the quality of the service can be conveniently increased throughout time until the network arrives to a continuous service provisioning mode. So we believe the value of this work is interesting and provides practical solutions for the design of future direct-to-satellite IoT networks. So thank you much for your attention. I leave my contact email address here, and I'm very happy to take questions or comments by in real life or by using this email. And with this, I complete my 15 minutes of presentation.